Here's a problem that stops a lot of models cold. Sometimes a network needs to make a hard choice. Pick a word, pick a codebook entry, pick an action, and then keep learning from that decision. But choosing the winner is an argmax, and argmax has no useful gradient. You simply can't backpropagate through a hard pick. The reparameterization trick rescued continuous sampling for the variational autoencoder, moving the randomness aside so gradients could flow. This one does the same magic for discrete choices, and it's the quiet workhorse behind training models that make categorical decisions end-to-end. Let's unpack how. First, let's pin down exactly why a discrete choice breaks gradient descent. Picking a category means taking an argmax, choosing the option with the highest score. That gives you a hard one-hot answer, a clean single winner, but it's a step function. Nudge the scores a little, and the choice usually doesn't move at all, and then suddenly it flips. There's no smooth slope for gradients to follow, so learning stalls. This technique replaces that hard pick with a soft, almost one-hot vector. It's mostly zeros with one value close to 1, near enough to a real choice to be useful, yet smooth enough that gradients flow right through it. Now the network can learn which category to prefer using ordinary backpropagation, the same way it learns any other weight. So how does the trick actually work? It comes together in a few clean steps. Start with the scores. Take your category log probabilities and add a dash of special Gumbel noise to each one. Random values drawn from the Gumbel distribution. This is the very same move as reparameterization, pushing all the randomness out into an external noise source you don't need gradients for. Now, in principle, you take an argmax. Picking the largest noisy score gives you a genuine sample from the original categorical distribution, an elegant fact known as the Gumbel-Max trick. The trouble is the same as before, that argmax is a hard, non-differentiable wall. So swap it out. Replace the argmax with a softmax at a chosen temperature. Instead of a hard winner, you get a smooth probability vector and gradients pass through cleanly. At a high temperature, the vector is soft and gentle, spreading weight across the options, which is easy for learning to shape and push around. Then turn down the heat. As you lower the temperature toward 0, that soft vector sharpens until it's almost a true one-hot sample, an ever crisper approximation of a real discrete choice. Anneal it over training, and you shift gradually from easy gradients toward genuinely discrete behavior. Strip it back, and 3 ideas define this trick. It makes discrete sampling differentiable. A choice that was a hard, gradient blocking wall becomes a smooth operation, so you can train models that sample categories with plain gradient descent. It adds Gumbel noise, then a temperature softmax instead of an argmax. The noise turns a fixed distribution into a genuine sample, and the softmax stands in for the hard pick while keeping everything differentiable. It trains discrete latents and tokens end-to-end. Discrete VEs, hard attention, learned tokenization, and neural architecture search all rely on it. A popular variant, straight through Gumbel, uses the hard sample going forward but the soft gradient coming back, and the temperature is your dial between crisp choices and useful gradients. All right, let's lock in what matters. This trick makes sampling a discrete category differentiable, so gradients can flow through a hard choice and models learn discrete decisions end-to-end. It works in 2 moves. Add Gumbel noise to the log probabilities to sample, then replace the non-differentiable argmax with a temperature softmax. High temperature gives a soft, very differentiable vector, and lowering it toward 0 sharpens the sample toward a true one-hot choice, so you anneal as training proceeds. It unlocked training discrete VEs, hard attention, and learned tokenization, with straight-through Gumbel a common variant. If ideas like this landing cleanly is what you're after, we explain a whole lot more over at standarity.com. See you inside.